Measures of Dispersion, Module 2, Part 3b. Throughout the videos, when you see the stop sign, pause the video and work the problem before continuing. In your serum HDL problem, you should have gotten a mean of 57.4 and a standard deviation of 11.7. We note that the distribution of the data is pretty much bell-shaped, or we would call that normally distributed. Excel can be used to do some simple statistics such as drawing graphs, sorting data, finding the mean or average, and sample standard deviations. Notice the standard deviation from Excel below is slightly different than the one on the previous slide because Excel only calculates standard deviations for a sample, not a population. Samples are more common, but in this class you may need to calculate population parameters as well. A good way to find out how to do something with your version of Excel, if you have one, is to search on Google or YouTube for the direction. In general, you should find a few statistical functions by clicking on the menu bar across the top of the Excel screen. You usually will see this summation, this sigma sign, and if you click on the arrow, it opens up functions so you can see you can sum a column, average, it'll count the numbers that you have, give you the maximum and the minimum, which is important if you're looking for range. And if you click more functions, it will open up this screen, and here you can see standard deviation. Part C, determine the percentage of patients that have serum HDL within 3 standard deviations of the mean according to the empirical rule. Well, the empirical rule says that within 3 standard deviations, you'll find 99.7% of the data in your sample. So that's the answer to this problem. The percentage of patients that have a serum HDL within 3 standard deviations of the mean would be about 99.7%. Now determine the percentage of patients that have serum HDL between 34 and 69.1 according to the empirical rule. And remember that our population mean was 57.4 and our standard deviation was 11.7 because we need to know that to make this calculation. So the mean is always in the middle, 57.4. The first bar to the right is 1 standard deviation. Well, a standard deviation for this data is 11.7, so we need to add 11.7 plus 57.4 to get 69.1. And we notice that's one of the values that we need. This other value, 34, is less than the mean, so let's go down to the left and see how far below the mean it is. So if we subtract 11.7 from 57.4, we get 45.7, so we need to go further. That's 1 standard deviation below the mean. If we take another 11.7 away, that gets us down to 34. So the problem is asking what percentage of the patients would be between this mark here, between the 34 and 69.1, because 34 is 2 standard deviations below the mean and 69.1 is 1 standard deviation of the mean. We can use the empirical rule. We know that 1 standard deviation above the mean is 34%, and 1 standard deviation below the mean is another 34%. The second standard deviation below the mean is another 13.5%. So this section here is 13.5%, and this section here is 34% of the data, and this section here is 34%. So when we add those up, we get 81.5%. So the answer to the question is that 81.5% of the patients had an HDL between 34 and 69.1. And we can tell that just by knowing that this data is normally distributed, that it follows that bell-shaped distribution, and knowing the mean and the standard deviation. So the empirical rule let us estimate the number of patients that had a serum HDL between 34 and 69. So let's go back to the actual data and see exactly how many there were. So I used Excel here and I sorted the data, and greater than 34, so actually the lowest value is a 35. And if we continue on, we're going to look for 69.1. And go down this column, 62, 63, 4, 5. Okay, here we hit 69. So 69 is less than 69.1. So all of those, if we count all of those, and you'll notice that Excel numbers things, don't get confused though and say there's 46 numbers because I used the first row for my header. So there's actually 45 numbers that are between 34 and 69.1 in the list. Unless the word inclusive is used, then we do not include 34 or 69.1, and that wasn't a problem in this case because they weren't actual data points. If you sort using the calculator, you can do the same thing, and you'll still find out that there are 45 observations between 34 and 69.1. So there were a total of 54 patients, so 45 out of 54, which is 0.833 if you do that on a calculator, and then of course moving the decimal 2 places to the right turns that into 83.3%. That's the actual value because that was a population and that was all of the data in that population. So we know 83.3% of the patients had serum HDL levels between 34.0 and 69.1. We used statistics to estimate, and the estimate was 81.5% from our empirical rule. That's pretty close to the actual value. Now, when you really do statistics, you rarely have the data from the whole population. So the reason we're going through these exercises is to show you that if you use the statistics, you get an estimate, and it's close to the real value of the population. But most of the time when you're doing statistics, you don't ever really know what the real value is. In fact, that's why you're using statistics, so you can use a smaller number in your sample to make estimates about the larger population. Make note that the password for Module 2 Part 3 assessment is disperse because you'll need it later. Here's another example. At a tennis tournament, a statistician keeps track of every serve. The statistician reported that the mean serve speed of a particular player was 103 miles per hour, and the standard deviation of the serve speeds was 9 miles per hour. Assume that the statistician also gave us the information that the distribution of the serve speeds was bell-shaped, because if we don't know that, we can't use the empirical rule. What proportion of the player's serves are expected to be between 112 miles per hour and 130 miles per hour? We're going to use that empirical rule, and if you haven't figured out you need to know that, you probably will by the time we get to the end of this presentation. So 103 is the mean, and it's going to go in the middle. And 103 minus 1 would be 1 standard deviation below the mean. But remember, a standard deviation is 9, so we want to take 103 minus 9, and we get 94. Goes in the first standard deviation below the mean, and 103 plus 9, 1 standard deviation of 9, gives us 112 for a standard deviation above the mean. 2 standard deviations below the mean, we can either subtract another 9 from the 94, or we could subtract from 103. Either way, 2 standard deviations below the mean gives us 85. 2 standard deviations above the mean, we can add 18 to 103, or we can add 9 to 112. Remember, each standard deviation is 9 miles per hour. That means 121 is 2 standard deviations above the mean. If we go 3 standard deviations, then we'll have 103 plus 3 times 9 is 27, so that gives us 130 is 3 standard deviations above the mean, or 103 minus 3 times 9 is 27 gives us 76 for 3 standard deviations below the mean. Now the question was, what proportion of the serves do we expect to find between 112 and 130? So we had to go all the way up to 3 standard deviations because that's where we find 130, and 112 is 2 standard deviations. So the percentage or the proportion is actually the area under that curve, and it is highlighted here in green. And using the percents from your empirical rule, the section between 1 standard deviation above the mean and 3 standard deviations above the mean, so in between here, gets that section that has 13.5% of the data, and that section that has 2.35% of the data. If we had 13.5 and 2.35, I didn't do a very good job of lining up my decimals. This would be a 5, an 8, and 15, so 15.85% of the serves we would expect to be between 112 miles per hour and 130 miles per hour. If we put that in decimal form because it asks for proportion and not percent, then we would say 0.1585 of the serves would be in that speed range. A small computing center has found that the number of jobs submitted per day to its computers has a distribution that is approximately bell-shaped. And again, we can't use the empirical rule if we don't have approximately bell-shaped or normal data. We also need the mean, which in this case is 91, and the standard deviation, which is 12. And if you've got data where that's not given to you, then you have to use software to find it. Where do we expect most of the distribution to fall? And most, they mean 95%. We know from the empirical rule that 95% of a distribution, if it's normally distributed, falls between 2 standard deviations below and 2 standard deviations above the mean. So stop and see if you can work this before you look at the solution on the next slide. Again, we need to use the empirical rule and its bell-shaped distribution curve and place the mean in the middle. Note that 95% of the data in any bell-shaped distribution falls between 2 standard deviations above and 2 standard deviations below the mean. To answer this question, we need to find out exactly what speed is 2 standard deviations below and what speed is 2 standard deviations above our mean. So our mean is 91, and our standard deviation was 12, so 91 plus 12, 103 is 1 standard deviation above. Add another 12 to that, or go back to your mean and add 2 standard deviations, which would be 24, to your 91. Either way is going to get you 2 standard deviations above is 115. Now work below. From the mean of 91, subtract 12, which is 1 standard deviation, and you get 79. Subtract another 12 and you get 67, or if you want to start with the mean, you can take away 2 standard deviations from 91, so 91 minus 24 also gives you 67. So most of the distribution, most being defined as 95%, will fall between 67 and 115 jobs. Solar energy is considered by many to be the energy of the future. A recent survey was taken to compare the cost of solar energy to the cost of gas or electric energy. Results of the survey revealed that distribution of the amount of the monthly utility bill of a 3-bedroom house using gas and electric energy had a mean of $119 and a standard deviation of $8. If the distribution can be considered bell-shaped, so we need those 3 things. We need to know the distribution is normal or bell-shaped, we need the mean, and we need the standard deviation, or else we need the data so we can determine those 3 things for ourselves. So now I want to know what percentage of homes will have a monthly bill of more than $111. Now stop and see if you can work the problem before you look at the solution on the next slide. Again, we're going to consider the bell-shaped curve labeled with your data. The mean will be in the middle, and you're going to go up 1, 2, and 3 standard deviations, or until you get the numbers that are of interest in your problem, which for us is 111. Since there is no right endpoint on this one, we're going to consider the percent above 111 on that bell-shaped curve. So our mean is 119, and our standard deviation is $8. So we put our mean down here in the middle. Our value of interest is 111. So we know that we need to go below the mean, not above. So below the mean would be 119 minus 1 standard deviation, so 119 minus 8 gives us 111, and that's our number of interest. The question was, what percentage would have a bill greater than $111? So we want to know what percent is represented by all of this portion greater than 111. And we know this bill is symmetric, so half of the data lie to the right of the mean. So this whole section here would be 50%. And we know this section, one standard deviation below the mean, is 34%. So the answer to this question is that 84% of the bills would be greater than $111. You could also add up all of the percents in the green area, the 34, the 13.5, the 2.35, and the 0.15, and arrive at 84% as well. Now complete Module 2, Part 3 Assessment of Learning. The password was given to you earlier in this presentation. I hope you were paying attention.